Let's look at the fundamental definition in section 1.3 vector subspaces. So a subspace of a vector space is a subset of a vector space that is itself a vector space under the same operations as the vector space. Okay, so a subspace is a subset and a vector space itself with the same operations. So let's look at some examples and non-examples. Here's a nice classic example. Here is a vector space. It is the set of polynomials of degree at most 3 with real coefficients. Okay, so what great subspaces of V could you think of? Well, here's the cheesiest one I can come up with. What about V itself? Technically a subspace, and yes, it satisfies all the vector space axioms because V was a vector space. Well, that's a little cheaty. What about this one? This is called the zero subspace. Also cheaty, but it's pretty classic, so we should talk about it. What about just zero? Like, well, this is a vector space, so it has a 0 element, and that's certainly a subset of V. Let's think about the vector space axioms. I have them here, so if you're trying to bring them up, okay, is this subset? Well, 0 plus 0 is going to be 0. 0 plus 0 plus 0 is equal to 0 plus 0 plus 0. We don't have any options here, right? Oh, wait, 0 is definitely there. What's the inverse of 0? It's 0. Yeah, okay, so this is also a subspace in the cheesiest possible way. And notice, neither of these actually depended on polynomials at all. So here's a note. V and the 0 subspace are always subspaces. Well, that's convenient. You get 2 for free anytime you want. Okay, so let's do something a little less trivial than those two. What about W equal to A3x3, where A3 is a real number? Okay, so you could think about elements here, like an element of here might be 2x to the third, or 7x to the third, or 136 pi x to the third, but those are what my elements look like. In other words, this part is 0, that part is 0, and that part is 0. So it is a subset here. Let's think about the axioms again, okay? Can you see that vector space 1, commutativity, is true for all vectors? So in fact, vector space 1 is, if it's true for all vectors, of course it's true for that subset. Associativity is the same way. Any 3 vectors satisfy associativity. So in fact, for any 3 vectors in W, they satisfy associativity. 1, 2, and actually the last 3, you essentially get for free. Notice this is true for any vector in V, in particular something in a subset. True for any vector in V, true for any 2 vectors in V, any vector in V. So 1, 2, and 5 through 8 hold for any vector. This isn't true of just this example. It's true of everything. So we don't have to worry about those. What we do have to worry about is the last 2. What about vector space 3? Well, that's the one, remember, that says I've got a 0. Is there something here that acts like 0? Well, yes, there is. How about 0x to the third? 0x to the third is equal to 0, and it's in W, and in fact, it works just like 0. What about vector space 4? Well, for any element in the set, okay, what would an element in the set look like? An element in the set might look like A3x to the 3. Is there some other element? Yeah, well, what about negative A3x to the 3? It's going to equal 0, right? So every element here has another element in W that gets back there. So yes, this is another subspace. I happen to do degree 3, but another example would be the constant terms, right? What if I just had A0, such that A0 is a real number? Same, right? These come for free. 0 is certainly in there. And if you had any real number, its inverse is also a real number. Well, let's look at the non-example. What would a non-example look like? What about constants where the constant was just greater than 0? Well, no, right? Yes, you actually get all of these axioms for free, but notice 0 is not in W. Well, that's no fair. I mean, we should just put greater than or equal to 0, so then that doesn't count. What about additive inverses? Well, if you had 7 is in W, -7 is not in W. So this doesn't work, right? This is not an example, even though the others were. So it's worth sort of thinking about what is an example and what isn't an example. Okay, one last example. Let's think about, what if you had any coefficient in front of the x squared term and any coefficient in front of the linear term? Oops, where these are both real numbers. Well, you can sort of check for yourself. Indeed, all of these axioms hold for free. If those were both 0, you would have 0, so you do have the 0 vector. And in fact, for any positive numbers, you could just add something that has the negative numbers. And this also is a subspace. So all of these are vector spaces in their own right, sitting inside the same old thing. What about matrices, m by n matrices with complex entries? Well, what could you do? You could have W be zeros on the top row, and everything else can be anything at once. AM2, AMN. Yeah, so this works just fine, right? Because adding any two of these elements gives you an element look right back there. Again, these axioms you get for free. If all of these are 0, obviously you have the additive identity. If you picked an element like this with non-zero entries, make them all negative, change the sign, and you would have an additive inverse. Okay, well, what wouldn't work? So this is a yes, and we're just trying to build intuition for what's happening here. What if you had something where one of these entries couldn't be, maybe everything was 0, but this entry was A11, such that A11 was, we already dealt with positive, that wouldn't work. What if A11 is only a real number? How about that? Well, that is not, and here's why. If you took some element in here, let's imagine you took the element 1, 0, 0, 0, 0, 0, 0, 0, you have to be able to scale by anything in the field. So I have to be able to scale by any complex number. What about 2i? Well, I can scale by that. It's just fine. I would multiply everything by 2i, and I get out 2i, 0, 0, 0, 0, 0, 0. The only problem is that is not in W. That's not how a vector space works. You scale something in a vector space, you get to the vector space. So this is another example of something that is not a subspace.